Across the deserts of northwest Saudi Arabia, one of the most ambitious energy projects in modern history is quietly taking shape. From space, it appears as another industrial development along the Red Sea coast. But beneath its vast network of pipelines, storage tanks, renewable power plants, and processing facilities lies an experiment that could redefine the future of global energy. Governments are watching, investors are watching, engineers are watching. Around the world, industries that depend on energy are watching closely. Because if this project succeeds, it could transform not only how hydrogen is produced, but how clean energy is traded across continents. This is the story of NEOM's hydrogen megaproject and why the entire world is paying attention. Every megaproject begins with one important decision: location. NEOM sits on Saudi Arabia's Red Sea coast, where some of the world's most powerful natural resources come together. Endless sunshine provides abundant solar energy. Strong coastal winds generate electricity day and night. Access to seawater supports large-scale desalination, while nearby ports create direct connections to Europe, Asia, and Africa. These advantages make NEOM more than just another industrial site. They create the ideal conditions for producing green hydrogen at unprecedented scale. Rather than transporting renewable electricity across oceans, the vision is to convert that energy into hydrogen, allowing clean power itself to become a globally traded commodity. Before a single kilogram of hydrogen can be produced, an enormous invisible system must operate flawlessly. Massive solar farms and wind turbines generate gigawatts of renewable electricity. That electricity then flows through high-voltage transmission lines into substations, transformers, switchgear, and powerful rectifiers that convert alternating current into the direct current required by industrial electrolyzers. This electrical network rarely appears in headlines, yet it is the backbone of the entire project. Every molecule of hydrogen depends on reliable power flowing through this hidden infrastructure. Without it, the world's largest hydrogen plant would simply be another collection of empty industrial buildings. At the heart of the facility stands the electrolyzer hall. Here, renewable electricity powers thousands of electrochemical cells that separate purified water into hydrogen and oxygen. The process is remarkably simple in principle, yet incredibly sophisticated at industrial scale. Water enters each electrolyzer, electricity passes through specialized membranes, oxygen is released, and pure hydrogen emerges ready for the next stage of production. Every hour, countless microscopic reactions occur simultaneously, transforming renewable energy into clean fuel. This is the moment where sunlight and wind are converted into something that can be stored, transported, and eventually power industries around the world. Producing hydrogen is only the beginning. Because renewable electricity naturally rises and falls with changing weather conditions, the hydrogen must be carefully managed after it leaves the electrolyzers. Powerful storage systems allow production to continue while creating a stable supply for downstream processing and export. These massive tanks act as the project's energy reservoir, balancing fluctuations in renewable generation and ensuring a continuous flow through the rest of the facility. They transform intermittent renewable energy into a dependable industrial product. It is this ability to store clean energy in molecular form that makes hydrogen fundamentally different from electricity, and one of the reasons why projects like NEOM have attracted worldwide attention. Behind every kilogram of green hydrogen is a resource that is often overlooked: water. Although NEOM sits beside the Red Sea, seawater cannot simply be pumped into an electrolyzer. It must first pass through an advanced desalination facility where salt, minerals, and impurities are carefully removed. Multiple stages of filtration and reverse osmosis produce ultra-pure water that meets the strict requirements of hydrogen production. This hidden infrastructure quietly operates around the clock, ensuring a constant supply of clean water for the electrolyzers. It is one of the most critical systems in the entire project, proving that the future of hydrogen depends not only on renewable electricity, but also on intelligent water management. In one of the world's driest regions, every drop must be carefully engineered, recycled, and protected. Freshly produced hydrogen occupies an enormous volume. To move it efficiently through industrial pipelines, storage facilities, and export terminals, it must be compressed to extremely high pressures. This is where some of the most powerful machines in the entire plant begin their work. Multi-stage compressors gradually increase the hydrogen pressure, while sophisticated cooling systems remove the heat generated during compression. Every valve, sensor, and pressure vessel must operate with extraordinary precision because hydrogen molecules are among the smallest in nature and demand exceptional engineering standards. Compression is often invisible to the public, yet it is one of the most energy-intensive and technically demanding steps in the entire hydrogen value chain. Instead of shipping hydrogen directly, NEOM converts much of its production into ammonia. Inside the ammonia synthesis plant, hydrogen is combined with nitrogen extracted from the atmosphere through the Haber-Bosch process. The result is a stable liquid that can be transported using existing global shipping infrastructure. This single engineering decision changes everything. Rather than inventing an entirely new worldwide transport system for hydrogen, the project leverages decades of experience in ammonia handling, storage, and maritime logistics. It transforms renewable energy into a globally tradable product, allowing clean molecules to travel thousands of miles before being converted back into hydrogen or used directly in industry. Once ammonia leaves the production plant, an entirely different system takes over. Pipelines transport the product to large storage terminals before specialized loading arms transfer it into dedicated carriers waiting at the port. These ships become floating links in a new global energy network, connecting Saudi Arabia with industrial customers across Europe, Asia, and beyond. Every port, shipping lane, storage terminal, and receiving facility becomes part of a much larger international supply chain. Just as oil reshaped global trade during the 20th century, hydrogen and ammonia have the potential to create new trade routes built around renewable energy rather than fossil fuels. At first glance, NEOM appears to be a single industrial development on the Red Sea coast. In reality, it represents something much larger. Success here could influence investment decisions across continents, accelerate hydrogen infrastructure, and demonstrate that renewable electricity can be exported in molecular form rather than through power lines. Industries ranging from steel manufacturing and fertilizer production to shipping, aviation, and heavy transport are closely watching the outcome. Governments see an opportunity to strengthen energy security while reducing emissions. Investors see the possibility of an entirely new global commodity market. Engineers see one of the largest demonstrations of integrated clean energy systems ever attempted. This is why NEOM is no longer simply a project. It has become a benchmark for the future of industrial decarbonization and the emerging hydrogen economy. Megaprojects are never built by a single company. Behind NEOM's hydrogen facility stands a vast network of engineering firms, technology providers, equipment manufacturers, construction contractors, financial institutions, and thousands of highly skilled workers. Every section of the project, from renewable power generation and desalination to electrolysis, ammonia production, storage, and export infrastructure, requires specialized expertise. Engineers design complex process systems that must operate continuously for decades. Construction teams assemble enormous prefabricated modules weighing hundreds of tons before integrating them into a single operating facility. Digital modeling, automation, safety systems, logistics planning, and precision manufacturing all work together to transform an ambitious vision into reality. While the headlines often focus on the finished project, it is this extraordinary collaboration behind the scenes that makes one of the world's largest hydrogen developments possible. Building the future requires extraordinary investment. With a price tag measured in billions of dollars, NEOM represents one of the largest commitments ever made to a green hydrogen project. That investment extends far beyond the hydrogen plant itself. It finances renewable energy generation, transmission infrastructure, desalination facilities, electrolyzers, ammonia synthesis, export terminals, shipping infrastructure, digital control systems, engineering services, construction equipment, and thousands of jobs. Every dollar supports the creation of an entirely new industrial ecosystem designed to operate for decades. Investors are not simply funding a factory, they are financing a new model for producing, storing, transporting, and selling renewable energy. If successful, this project could demonstrate that large-scale green hydrogen is commercially viable and encourage even greater investment across the global energy transition. Constructing advanced industrial infrastructure in one of the world's harshest environments presents challenges unlike those faced by conventional projects. Summer temperatures regularly exceed 50 degrees Celsius. Dust storms reduce visibility and place constant stress on sensitive equipment. Water is scarce, requiring highly efficient desalination and recycling systems. Every material must withstand corrosion, intense ultraviolet radiation, thermal expansion, and abrasive desert conditions. Engineers must also solve complex logistical challenges associated with transporting massive equipment into remote locations while maintaining strict construction schedules. Every pipeline, electrical connection, cooling system, and structural component is designed with these extreme operating conditions in mind. NEOM is not simply a hydrogen project. It is an engineering demonstration of how advanced industrial systems can thrive in one of the planet's most demanding environments. Scale changes everything. Unlike conventional industrial facilities built piece by piece, NEOM relies heavily on modular construction. Entire process units are manufactured off-site, fully assembled, tested, and then transported to the project location for installation. Tower cranes capable of lifting hundreds of tons position these massive modules with remarkable precision, allowing construction teams to reduce installation time while improving quality and safety. Thousands of workers coordinate around the clock as civil works, electrical systems, mechanical installation, instrumentation, and commissioning activities progress simultaneously across the site. Looking across the project, it becomes clear that this is far more than a construction site. It is a carefully choreographed industrial operation where engineering, logistics, manufacturing, and project management converge on an unprecedented scale. Producing clean hydrogen only makes sense if customers are ready to buy it. Around the world, governments and industries are searching for practical ways to reduce carbon emissions while maintaining reliable energy supplies. Europe is investing heavily in clean industrial fuels to support steel production, chemicals, and manufacturing. Japan and South Korea view hydrogen as a strategic component of future energy security. Shipping companies are exploring ammonia as a low-carbon marine fuel, while fertilizer manufacturers seek cleaner production methods. Heavy industries that cannot easily electrify are increasingly turning toward hydrogen as one of the few realistic pathways to decarbonization. NEOM is positioning itself to supply these emerging markets, transforming renewable energy generated in the Saudi desert into a globally traded product capable of supporting industries thousands of miles away. NEOM may be one of the largest hydrogen projects ever attempted, but it is far from the only one. Across the globe, governments have recognized that the transition to clean energy represents not only an environmental opportunity, but also an economic one. Australia is investing heavily in renewable-powered hydrogen exports to Asia. Chile is leveraging its exceptional wind resources in Patagonia and abundant solar energy in the Atacama Desert. Oman and Namibia are developing coastal hydrogen hubs designed to serve international markets, while Canada and the United States are accelerating hydrogen production through major public and private investments. Europe is simultaneously expanding domestic production while building import infrastructure for future hydrogen supplies. What has emerged is no longer a collection of isolated projects. It is a global competition to become the leading producers, exporters, and technology innovators in the hydrogen economy. Countries are not simply racing to build hydrogen plants, they are competing to shape the next generation of global energy markets. Despite the excitement surrounding hydrogen, success is far from guaranteed. Every megaproject must answer difficult technical and economic questions before it can prove itself over the long term. Can renewable electricity remain affordable enough to produce competitive hydrogen? Will electrolyzers continue improving in efficiency while reducing costs? Can desalination systems provide reliable water supplies without creating new environmental pressures? Will enough customers commit to purchasing hydrogen and ammonia at commercial scale? Even shipping, storage, regulations, and certification systems continue to evolve. These uncertainties represent the true test facing projects like NEOM. The challenge is no longer proving that hydrogen can be produced. It is proving that the entire value chain can operate reliably, economically, and competitively for decades. Success will depend not on a single technology, but on the performance of every connected system. If these challenges can be overcome, the opportunities extend far beyond one industry. Hydrogen has the potential to become a foundational energy carrier for sectors that are difficult to electrify. Steel manufacturers could replace coal with hydrogen to dramatically reduce emissions. Shipping companies could transition toward ammonia-based fuels for long-distance transport. Aviation may increasingly rely on hydrogen-derived sustainable fuels for future aircraft. Fertilizer production, one of the world's largest hydrogen consumers today, could become significantly cleaner by replacing fossil-based feedstocks with renewable hydrogen. Heavy manufacturing, mining, cement production, chemical processing, and long-haul transportation could all benefit from abundant supplies of low-carbon hydrogen. Rather than replacing electricity, hydrogen complements renewable power by providing energy storage, industrial feedstock, and transportable fuel for applications where batteries alone may not be practical. The significance of NEOM extends beyond its own boundaries. Around the world, dozens of new hydrogen megaprojects are already moving from concept to construction. Countries with exceptional renewable resources are beginning to identify locations where future hydrogen production could become a major economic opportunity. New export terminals, pipelines, storage facilities, industrial clusters, and shipping routes are gradually forming the foundations of a global hydrogen network. Every successful project contributes valuable engineering knowledge, improves supply chains, lowers equipment costs, and increases investor confidence. Much like the early development of the liquefied natural gas industry decades ago, today's hydrogen projects may become the starting point for an entirely new global energy system. NEOM is not the destination. It is the beginning of a much larger transformation. The next decade is likely to determine whether hydrogen becomes a mainstream global energy commodity or remains a specialized industrial fuel. A new generation of projects is already emerging across Australia, Chile, Namibia, Oman, Canada, the United States, and many other regions rich in renewable energy. These developments will build upon the engineering lessons learned from pioneers like NEOM while benefiting from improving technology, expanding infrastructure, and growing international demand. Together, they have the potential to create entirely new hydrogen trade corridors linking renewable-rich regions with industrial economies around the world. The hydrogen economy is no longer defined by a single project or a single nation. It is becoming a worldwide movement driven by innovation, collaboration, and the pursuit of cleaner, more resilient energy systems. What happens next will shape the future of global industry for generations to come. For more than a century, the global economy has been built around the movement of oil and natural gas. Tankers crossed oceans carrying fossil fuels from resource-rich regions to industrial economies, creating trade routes that shaped geopolitics, economic growth, and international relationships. Hydrogen now presents the possibility of a new chapter in global energy trade. Instead of exporting carbon-based fuels, countries blessed with abundant renewable resources could export clean energy in molecular form. Hydrogen and ammonia could move through shipping networks much like oil does today, supplying industries that cannot rely solely on electricity. This shift would fundamentally change how nations think about energy security, creating new opportunities for countries capable of producing renewable power at massive scale while reducing dependence on traditional fossil fuel markets. If projects like NEOM achieve long-term success, their influence will extend far beyond the energy sector. Green hydrogen could become a cornerstone of industrial decarbonization, helping manufacturers produce steel without coal, enabling cleaner chemical production, supporting sustainable aviation fuels, and powering the next generation of zero-emission shipping. Mining operations, cement plants, refineries, fertilizer manufacturers, and heavy transportation networks may all become connected through a shared hydrogen economy. Entire industrial clusters could emerge around reliable supplies of renewable hydrogen, attracting investment, creating new jobs, and accelerating technological innovation. Rather than replacing existing industries, hydrogen has the potential to transform how those industries operate, reducing emissions while maintaining the productivity needed to support growing global economies. NEOM represents far more than an engineering achievement or a large construction project. It serves as a real-world demonstration of what is possible when renewable energy, advanced manufacturing, digital technologies, global investment, and international collaboration come together around a common goal. Every lesson learned, from renewable integration and water management to electrolysis, ammonia production, logistics, and export, will influence the design of future hydrogen facilities around the world. Even if every challenge is not solved immediately, The knowledge generated by this project will shape future investments, improve engineering practices, strengthen global supply chains, and help reduce the cost of future developments. This is why so many governments, researchers, investors, and engineers continue to watch NEOM closely. It is not simply testing a new technology, it is testing a new model for the future of industrial energy. The story of hydrogen is only beginning. Over the coming decade, new technologies will improve efficiency, larger projects will come online, international regulations will mature, and global trade networks will continue to expand. Countries that invest today may become tomorrow's leaders in clean energy exports, while industries that adapt early could gain significant competitive advantages. Every successful project creates new engineering expertise, lowers technology costs, and increases confidence across the market. The hydrogen economy will not emerge from one project alone, but from hundreds of interconnected projects built across multiple continents. What happens next depends on continued innovation, collaboration, and the willingness to transform today's ambitious ideas into tomorrow's operating infrastructure. The decisions being made today will influence how the world produces, transports, and uses energy for generations to come. Understanding projects like NEOM requires more than reading headlines or following industry news. It requires understanding the hidden systems that make these projects work, from renewable energy and electrolysis to storage, ammonia production, global logistics, engineering design, and project economics. That is the mission of H2 Hub by ReneEnergy. Through interactive learning, engineering schematics, financial analysis, real-world project intelligence, AI-powered exploration, and expert educational resources, H2 Hub helps engineers, students, investors, developers, and energy professionals understand the technologies shaping the future of hydrogen. As new projects emerge across the world, the opportunity to learn has never been greater. The future of clean energy is already being built. The question is no longer whether hydrogen will play a role. It is how prepared we will be to understand, design, and participate in the systems that will define the next generation of global energy. Welcome to H2 Hub by ReneEnergy, where the future of hydrogen begins with understanding the engineering behind it.